Hello, my name is Martin Beisel, and in this video I'll present a standards-based toolchain to model and execute quantum workflows. The increasing availability of quantum devices via the cloud led to a multitude of commercial and scientific tools for developing quantum applications. However, since quantum applications are typically hybrid, comprising both quantum and classical parts, these tools are very heterogeneous. Therefore, combining them within a single application is complicated by incompatible programming languages, data formats, and interfaces. Hence, to enable the development of portable and interoperable quantum applications, a standards-based toolchain is required. In this demonstration, we present a holistic toolchain for developing quantum applications utilizing well-established standards for defining workflows, deployment topologies, application interfaces, and provenance data, namely BPMN, Tosca, OpenAPI, and the Prof standard. In the following, we present our system architecture and demonstrate the prototype, realizing it for a typical quantum computing use case from the machine learning domain. To model quantum applications, we utilize the QuantMe framework. The QuantMe modeler is a BPMN 2.0 based modeler, which was extended to support the quantum modeling extension QuantMe, which provides quantum-specific modeling constructs for commonly occurring quantum tasks. To ensure portability, these modeling constructs can be transformed to native BPMN modeling constructs utilizing reusable workflow fragments. To execute these BPMN workflows, the well-established Camunda workflow engine is used, which was extended to support role-specific process views, facilitating the understanding of the workflow by utilizing provenance data available in QProf, a provenance system supporting the Prof standard. The quantum service generator is used to generate required quantum services during runtime based on OpenAPI specifications supporting the quantum service extension. To model deployment topologies and orchestrate them, the Open Tosca ecosystem is used. Binary enables the modeling of Tosca deployment models using a wide range of node types, and the Open Tosca container is capable of orchestrating these Tosca deployment models. Now let's get to the prototype realizing this architecture. To execute the exemplary workflow, simply open the corresponding BPMN file from the GitHub repository. As you can see, the workflow comprises 4 QuantMe tasks and 1 user task for analyzing the process after execution. The first task is the circuit loading task, which is used to generate the quantum circuit utilized for solving the maximum cut problem. Afterwards, the quantum circuit is executed by a circuit execution task, and the execution results are subsequently evaluated by a result evaluation task. As variational quantum algorithms, such as the quantum approximate optimization algorithm used in this use case, rely on the iterative optimization of circuit parameters to find good solutions, a gateway condition is used to check if the parameter search is already converged. If the search is not converged yet, a parameter optimization task is used to find more suitable parameters which can be applied in the next iteration, circuit execution. Once converged, the user can analyze the final result. To execute the workflow, our QuantMe modeling constructs need to be transformed into native BPMN modeling constructs. Thus, we need to click on Transformation. For the circuit execution, a subprocess was added, which initially generates and deploys the required service during runtime, such that it can be used for all future iterations. Quantum circuit generation, result evaluation, as well as parameter optimization require the deployment of dedicated service instances. The corresponding deployment models can be viewed by clicking the respective icon. As you can see, we deploy the service on an open stack using a Ubuntu VM, and we need to install Python and Qiskit. To deploy the required services, we now click on Service Deployment, and then confirm the deployment topologies that we want to upload. Once the deployment models are uploaded to the Open Tosca container, we need to enter the required credentials. Once all credentials are filled into the form, we can click on Deploy Services. This might take a few minutes as the service instances need to be created and all requirements need to be installed. Once all services have been deployed, the endpoints must be bound to their respective tasks by clicking on Perform Binding. Finally, since all QuantMe modeling constructs have been transformed and all services have been deployed, we can now deploy the workflow to the workflow engine. We do this by clicking on Deploy Workflow. And as you can see, the workflow has successfully deployed to the workflow engine. Now, let's head over there. To instantiate the workflow, we need to go to the task list. There, we can start the process by selecting our workflow and then entering our problem instance as well as the credentials and the starting parameters. Then we click on Start to initialize the workflow. And as you can see, the workflow has been started. Then we can head to the Camunda cockpit, select our workflow again, select the workflow instance, and as you can see, currently the service for executing the quantum circuit is being generated and deployed. As this takes a few seconds, we now need to shortly wait, and then we can refresh to see the current state of the workflow. Now the circuit is being executed. And if we reload again, we can see that the optimization is in progress. And we are currently in the third iteration. If we now wait and reload again, you can see that we are now in the sixth iteration. And to observe the workflow in more detail, we can switch to the quantum view. As you can see, we can now observe the workflow in its original form before the QuantMe workflow modeling constructs were transformed into native BPMN modeling constructs. Further, we can analyze these QuantMe tasks in detail. Therefore, we hover over the respective task. And as you can see here now, we have the optimization history with its landscape that we can now observe in detail and see the optimization path that was taken by the optimizer. If we now reload, we can get an updated diagram. As you can see, we are now in the 26th iteration, and the optimization has continued to improve the parameter values. Further, we can analyze the current result by hovering over the result evaluation task. Here, we can see a graphical representation of the problem instance, a weighted, fully connected 6-node graph. The vertices are colored blue or red, depending on the partition computed by the quantum algorithm. The optimization goal is to maximize the value of the edges cut by the two partitions. As you can see, after reloading, the workflow has finally terminated after 30 iterations. We can observe the final result again in the result evaluation task. This concludes this demonstration video. Thanks a lot for your interest in our research.